right. Good afternoon and welcome to the second Heidelberg Joint Astronomical Colloquium in the summer term 2025. And with great pleasure, I welcome Mario Flock from the Max Planck Institute for Astronomy up the hill over there. And we will learn everything about rim worlds and computational astrophysics of accretion disk before we go to the astrophysics and astronomy of protoplanetary, I suppose, accretion disks. Black hole also?
Protoplanetary.
Okay. Protoplanetary accretion disks. Let me introduce the speaker briefly. You actually did study here. Yes. I see the master here at Heidelberg University and then the PhD, again here in Heidelberg, with PhD work done up at the Max Planck Institute. Then you went to a place that many of us also know, and in fact many of us go next week to Circumstellar, to the CAA, and you spent about 3 or almost 4 years there, and then you went over the pond and the landmass of the North American continent to work at Pasadena at the NASA Jet Propulsion Laboratory and Caltech first. And Mario came back to Heidelberg to take on a, I shouldn't say junior research group position, but the position as a group leader at the Max Planck Institute for Astronomy, funded by the ESC grant, and this is where you have been since. Yes. And so I think we will learn from some of the work you have done in the ESC grant today. Yes. So welcome, Mario.
Thanks, Ralph. Yeah, thank you very much for coming today. So good afternoon. So I'm happy to present you the news, so the recent results, what we did here in my group up the hill about computational astrophysics of accretion disks. And as Ralph mentioned, it's about circumstellar disks. So, but let's first explain the title. So why rim worlds? So it has nothing to do with this video game, which is actually called Rim World. Never played it, but has something to do with astro. It has also nothing to do with the outer rim of the Star Wars universe, but we are coming closer. It's actually the inner rim. So this is just to move this up front. So what you see here is a sort of temperature plot. What we studied in this work is actually how this temperature and density environment can actually have an influence on sort of planet formation and also on inboard migrating planets. And in this study, we found that close to the silicate sublimation region here in the front scene, we have a very robust trap for not only solid material, but also for migrating planets. And this matches quite well, you know, the constraints which we have from the Kepler mission. So most of the innermost planets from multiplanetary systems are actually located at around 10 orbital period. And that is also what we found in this theoretical study. But not so fast, let's go back. So our team. So you can see here 2 figures, so the 2 photos which we did actually on the summer party, the MPA summer party. So it's very important, you know, to attend this soccer tournament, which we have every year there. And I will focus here on the sort of the first generation. So Liz and Marcelo, they did the PhD here, and they moved on now to MIT Boston and Uni Copenhagen, and I will present mainly the work which they did during the PhD. And you can see from last year, you know, we upgraded. We have now really soccer shirts, and this is now the second generation, which will continue in this area. Okay, so our tools, we use the Pluto code. So the Pluto code is a numerical software which was written by Andrea Mignone. It's a Godunov type code, so it's a shock capturing scheme. It contains many modules, many geometries, as it is here seen, a spherical grid. It's a CMPI code, and will soon port to GPU. So this is how we do our work. We set up our models on this Pluto code, we run those, and then we post-process and analyze this with Python. And also, if we want to compare with observations, we actually then include RADMC3D. So we include the models, post-process them with Monte Carlo radiative transfer, And then we are able to compare and test our models with observations. Okay, I will only briefly go over these equations. These are the basic ideal MHD equations, which are solved with the Pluto code. You can see a mass conservation, momentum conservation, the energy equation, and the MHD equations. And the goal now in the last 15 years was to include more and more physics. So we included more non-ideal terms, so included a better match of the magnetohydrodynamics. We included radiation transfer to study here the irradiation and also the flux limit diffusion. And we included particles. So we included the dust motions and also momentum feedback by the dust grains. And this will ongoing. So we try really to include more and more physics to make these simulations more realistic. Okay, our playground. So as I mentioned, we are working on circumstellar disks, especially gas and dust dynamics and the MHD instabilities, and also the dust-gas track instabilities. And now I will introduce a bit more about why it is so important to understand this gas accretion, or in general, the gas evolution of these circumstellar disks. So it actually goes back, 200 years when Kant and Laplace came up with this nebula hypothesis. And it was amazing that they already had these early ideas how disk is formed. So the formation of disk around the contracting nebula. And this idea is still sort of valid today. So the picture is that you start with a molecular cloud, which contracts, which due to the self-gravity collapses. So material is falling onto the protostar, but most of the material cannot directly fall onto the protostar because of the angular momentum conservation. So you end up with a fast rotating disk around this protostar. And once this envelope is gone, then we end up in a sort of circumstellar disk where there is gas and dust material. And this is the phase we want to study actually. And then finally, if the gas disk is dissipated, then we are left with the debris, with the dust debris. And that is what we then call the debris disk phase. Okay, a bit more about the gas disk evolution. So in this plot, you see here the mass accretion rate onto the star over age, both in log scale. And that's a sort of our understanding today how actually gas is accreted onto the protostar. So we think in the first phase, in the phase where you still have the collapse, the infalling envelope, the accretion is extremely bursty. So you have accretion bursts, and this is because gravitational instability is active, heat is trapped, and you have strong variations in this accretion phase. And you see here, once the envelope is sort of dissipated, so most of the mass is falling onto the disk, then we enter this Tauri star phase. So here, the variations in the accretion rate goes down, becomes more smooth, and this is the phase actually where where it is the big business for planet formation. This phase lasts for around 5 to 10 million years, and this is where we want to understand planet formation. Where we want to understand the gas and the dust dynamics in detail. And then once the disk is gone, then we enter the debris disk phase, and this is then where the terrestrial or the gas giants are already present. Okay, let's focus now on this disk. So I show here this equation, which is a sort of equation which is typically used for planet formation models, for 1D models. Just to get you an idea, the accretion rate, of course, depends on many parameters. So it depends on the mass, on the local surface density. It depends on the mass of the star because of the rotation speed of the disk, on the characteristic radius. It depends on the sound speed, here, the scale height, h/r. But most importantly, it depends on this alpha parameter. This alpha parameter is a parameter which was introduced many, many years ago. I will introduce that later. But it's basically traces, how turbulent the disk is. And we have here, last year we published a chapter in this Protostar and Planets. So it's a sort of review book, which is, every 7 years published, and we sort of summarize all the details, about the gas and dust dynamics. So I reference you to this work. Okay, but let's come now to alpha, to gas accretion. So this question was actually there since several decades. You can see here the work or the abstract entitled from Reimer Lüst. So he did his PhD back in 1950 at the Max Planck Institute in Göttingen. And the director was Werner Heisenberg, and due to his 50th birthday, he had this paper. It was still published in German, but what is fascinating, the basic idea was already formulated here. So because of the friction, you need friction to transport angular momentum through the disk. And this was the basic concept. So the concept, how can actually the gas accrete onto the star? But back then, they had just no idea, what physical mechanism can cause this friction, because the molecular viscosity, of pure hydrogen and helium is way too small. So they really were here looking in the dark. And it took 20 years when Shakura and Synaev came up with this fascinating idea. If you have turbulence, the turbulence acts as a stress. So you can write a stress tensor, and then they derive this alpha parameter. So the basic idea is if you have turbulent motions, like this here summarized, the turbulent azimuthal and radial fields, so this is density and pressure. And if you have magnetic fields, they both can act as a sort of effective viscosity, how they formulated it. And this is then, with this mechanism, that you could then explain for the first time, consistently the transport of angular momentum. You see that, this paper has over 11,000 citations. It's really important for many, many areas in astrophysics. But what is now interesting, back then, they had this nice concept, but actually they were also lacking something, and they were lacking actually the physical mechanism to produce the turbulence. So it's funny, in Lys, they were lacking the sort of idea, the concept. Then in Shakura and Synaev, they were lacking the physics, and it took another 20 years. And actually, Steve Balbus and Hawley came up with the idea, if you have weak magnetic fields, you can actually very efficiently generate turbulence by the magnetorotational instability. So this is instability, which is very robust. So you need only a high ionization, you need shear, you need a sort of weak magnetic field, which is amplified, and then you can generate turbulence. And this alpha value, which you generate due to this turbulence, matches actually quite well the values which are actually needed for the disk evolution. So how does it work? Here, small sketch. You have a gas parcel. This gas parcel is rotating a bit subcapillary because of the additional pressure gradient. So let's take another one, which is a bit outer. They are connected by this magnetic field. So they move apart because the inner one rotates faster than the outer one. But the magnetic field wants, actually the magnetic tension wants to pull these two gas parcels together. So which effectively means that you reduce, or you slow down this inner gas parcel and you speed up the outer one. So that means they will lose their stable orbit, they move even further apart, and then the magnetic field is even further amplified. So that's sort of the basic concept of the magnetorotational instability. And again, you need a weak magnetic field. You see here plasma beta, which is the ratio of gas pressure or magnetic pressure. So if beta is larger than unity, it means that the gas pressure dominates. You need shear and you need a high enough ionization. So this is a movie which I want to show to give you an idea about this basic concept. So this is a 3D simulation which we did. So you should see turbulent velocities here. This is 1 to 10 AU disk. It's a fully stratified model. So that means you also include the vertical gravity forces. And then you see here the turbulent velocities of a fully MRI, saturated disk. The sound speeds and the midplane are at around 10%. You can see these density waves going up and down. And then you have also here the turbulent velocities in the upper layers, so in the low density regimes, reaching up to 40%. And then if you move to the plasma beta again, as I mentioned before, so you can see very high values here at the midplane layer, so around several hundreds to 1,000 beta value, meaning that the magnetic field remain actually small, even if you have full MRI operating here. But then due to the buoyancy of the field, you can see that in the low density regime, actually the plasma beta of the disk corona goes down, so meaning the magnetic field becomes more important there. Okay. What we got out back then were then this plot here, so alpha parameter, you can then calculate this Reynolds and Maxwell stress. And what we found is that in the saturated accretion phase, you end up with values of 10 to the minus 2. So these values are actually, which are actually needed to explain this disk evolution. But we also found that if you add non-ideal terms, then the MRI efficiency goes down to values of 10 to the minus 4. So we had here this regime between 10 to the minus 4 and 0.01, where you could sort of operate with the MRI. Okay, so let's go back to this picture. I mean, there was a big step in this sort of history when, you know, let's say in 91, you know, for 20 years, people worked on the MRI. But then there was the PP6 chapter here by Neil Turner in 2014. That was a big step because now it became clear that most of the disk is actually under effect of very low ionization. So the MRI actually works only in a sort of narrow regime in the disk. And that was pushing a lot of research works now in the direction of a magnetic driven wind. Because if you have magnetic fields, what you automatically have is a strong torque, you know, from the magnetic field at the surface layer of the disk. And this is what was sort of neglected in the past. I mean, it was known, but it was sort of neglected. And that drove now or changed the picture that you have now the MRI and this magnetic driven wind together. Okay, here's a sort of a sketch how this looks like. So the sort of idea what we have, so you have the MRI in a regime here inwards, so inwards 0.1 to 1 AU, you need around 1,000 Kelvin or above. Then you have the magnetic driven wind operating here in these upper layers where the gas is ionized. You also have probably the MRI in the outer regime because of the cosmic ray ionization and the FUV ionization. And then there's this big regime here, which we call dead zone. So this is a zone with low ionization where the MRI cannot operate anymore. But there's one thing I want to make here clear is the scales. I mean, this is log R and this is C over R. What does it mean? So if you ever see a plot like that, you should be careful. Because what you see here is a sort of sketch of temperature of a disk. And you see it's in cylindrical geometry, so it shows you Z over radius. So if you ever see a linear plot of a disk, you should ask questions, because this shows you only part of the picture. What you actually can imagine, you know, if the disk starts at 0.1 AU and you want to look at this, you need really a high resolution to see what's going on in there. So the first thing you do a logarithmic grid in radius. Well, that's probably not enough. I mean, it helps you, but these scales are still very small. And the second step, what you do is you divide now this height with the local radius. And this is then where we are. And that's actually the reason why we use spherical grid, because you see already that COR is a good representation of the theta angle in spherical geometry. So with this geometry, you can actually probe, you know, the density and temperature structure quite well in these disk systems. And what you are here looking at is, again, sort of the gas and dust temperature field of an Herbig type star. You see this dust rim here at around 0.3 AU. This is location where we expect, again, this strong trap of pebbles and actually small planets. This is the ice line regime. And here we also include now the beta 1 area. So in this part, you know, magnetic fields would dominate, would cause a wind. And here you are still dominated by the gas pressure. Okay, but this is what I wanted to really that you know, this regime is very small compared to this. So the scales are really different. And therefore, yeah, you have to be careful when you see this plot. Okay, I will now move to the ionization transition regimes. So I told you it was found that the MRI works only in certain regimes. But now, if you think back on the alpha parameter, if you have changes in alpha, let's say you have here low alpha, you have a high alpha, these changes in alpha induce strong perturbations in the surface density. And these are crucial because the changes in the surface density cause changes in the rotation velocity, and they lead to very, very efficient particle trapping. And that's actually where we think where the first planets are formed. So we think that, you know, when you have the formation of a disk, this situation should be there right away. And we think that these are really the locations where the first planets can actually form. Okay, So this is a model I wanted to show you. So it's a model where we included now this sort of outer dead zone regime. So we are looking now here. So this is sort of the MRI damped regime. It becomes visible in this smooth picture here. So this shows the toroidal magnetic fields in milligauss. You see that there are strong current sheets here at the upper layers of the dead zone. But basically what we can extract from these simulations are strong changes in the turbulence. And these again will automatically lead to these pressure variations or surface density variations. And that's actually what we found. So we found these pressure variations, and then in the next step, we thought, well, let's now add particles, grains, which actually emit at different wavelengths. So that's what we did. And then we found this picture here. So this is a synthetic ALMA observation. So we are making here already 2 steps in front. So the same simulation I was just showing, but now with dust grains and with a sort of synthetic observation. So including a certain distance, including a certain configuration with the ALMA telescope. And we could actually find this sort of dust rings and gaps. So the message was here that perturbations by magnetic fields were able to cause this sort of ring and gap structures. And of course, we were lucky because it was the sort of same year where there was this famous observation of HL tau by the ALMA telescope. And yeah, I mean, we didn't want to say that every ring is here caused by magnetic fields, but it plays a very, very big role, especially for very young systems. Okay. Now, I mentioned to you this big paradigm change that there was now the MRI was probably not so important. Now the magnetic wind was more important, but that gave rise to the hydrodynamical turbulence. So in the last 6-7 years, a lot of groups studied hydrodynamical turbulence. So what happens if the magnetic fields actually don't have a big influence on the dynamics? So let's see where Liz's work come into play. She studied this in a sort of high resolution 2.5D axisymmetric setup with radial and vertical density stratification. And she was focusing on this vertical shear instability. The vertical shear instability is a pure hydrodynamical instability, but it requires a fast thermal relaxation. What does it mean? It means when you are, for example, here in the optical thick part of the disk, so we have a lot of mass, a lot of dust, radiation cannot escape easily. There you would not, the VSI would not operate. And also in the outer part, which are extremely optical thin, there also the VSI would not operate because the cooling and heating times are way too long. But there's this sweet spot in the disk where actually the disk becomes optical thin, so where the optical depth is around 1, and this is where the VSI can operate quite efficiently. And in this movie here, which shows you sort of the dynamics of the disk with fully VSI operating, so it's a line integral convolution plot. And we are looking here really at a cut through the disk. So these are the upper layers. And you can see these large scales which are going up and downward. So the whole disk is shaking up and downward. And when we saw that, I mean, the immediate question was, can we actually observe this? And this is, of course, when you look at the dust, it's quite difficult. I mean, of course, you can think of the dust grains, are here mixed up quite efficiently, but it's extremely difficult because often in continuum, you're only sensitive, right, to the upper layers. So, and that is when Marcelo Barraza came, and what you wanted now to do is actually to look for molecular line emission. So what you can do is you can say, well, how would, when you look at 12CO, how would the disk look like? So when you look at 12CO, you are tracing usually a very narrow slice at the upper disk. And then you can, because of ALMA has such a good spectral resolution, you can actually see these changes here. So these bulk motions going up and down, what you will actually see, because the spectral line of 12CO is actually shifted, either blue or red shifted. And this is actually what then Marcelo did. So this picture here shows you sort of the synthetic observation of a 12CO emission of a sort of VSI simulation. So the VSI is in fully operation mode. And what you see here with these red and blue stripes, these are exactly these up and downward going motions. So this is actually, this was showing already that ALMA is actually able to see the kinematics directly. So for the first time, we don't have to rely anymore on any dust mix. We could actually see the kinematics directly, and that was fascinating. That, you know, with sort of 10-hour observation with ALMA, which is of course quite long, but you are still able to capture this gas kinematics. But there's a catch to that, and the catch is actually to this part here. So you have to subtract a very good model, you know, because of course in first order you see the Keplerian rotation, so you have to remove that, and then you are left with this residual, which works good if the disk is face on, because then you automatically probe only this component. But if you have a inclination of around 40 degrees, so it gets really difficult to remove this rotation. So because you have to fit, you know, the rotation at this surface where actually the emission is coming from. But we were also lucky again, because this sort of similar year, Richard Teague actually observed the gas kinematics with such a technique. So you see here an observation of MWC 480. So it's a system, a star disk system, and you could see this sort of, you know, axisymmetric motions going up and downward. And actually what I found impressive is that it matches, you know, not only the scales, but also sort of the absolute values. So you can see that this here at around 60 meters per second upward and downward motion were also reached in this residual plot. So it was quite impressive that, you know, the scale and the magnitude of this perturbation matches very well. And this is, for example, then a disk which could, of course, be, I mean, caused by the VSI. But most of the observers, they actually don't want to hunt for the gas kinematics, they want to see planets, right? So they, of course, they were trying to argue, well, perhaps here are some embedded planets, but it's actually not so easy. So in the next step, what we did is we added a planet in this VSI simulation. So this is a very recent work where there's again a 3D model of the VSI, but you can see here 3 models. So without a planet, with a Jupiter mass planet, and with a Saturn mass planet and a Jupiter mass planet on the right. And you can see here, especially in the Saturn mass planet, so it's located here, it's really hard to observe the kinematic tracers here. What happens is actually, it's funny that the induced sort of vortices and spirals by the planet actually damp the VSI. When you compare these two plots, you see here the fully VSI active model shows these strong motions, but then this, in this case, it looks actually much more calmer, you know, much smaller turbulent velocities. And of course, when you go then to a Jupiter mass planet, then the effect is clear, right? You get this, what you expect, this perturbation, this strong perturbation here, local close to the planet, which can actually then be used to trace back the embedded planet. And again, what I want to remind you again, what we are looking here is really at the surface of the disk. So it's not straightforward actually that we see an effect, because, you know, we are really looking at 2-3 scale heights, but actually the planet is at the midplane. So therefore, it's in these 3D models, it's really difficult. But there's now this large program going, so ExoAlma, and the goal of this ExoAlma large program is really to identify exactly this here on the right. So this gas kinematics, which can explain then for example, where Jupiter mass planets are located in the disk. Okay. Now let's move on. So I was talking a lot about the gas. Let's go to the dust. So the dust is important, of course, for observations. So you see here a gallery of very famous disk observations. This is already an older one from the Hubble Space Telescope. So it shows you an edge-on protoplanetary disk. You see here the backscattered starlight. There's also here a jet indicated in green. And what is nice is you can see this flared disk. So we can really already make out the shape of the disk. And also this one here from Henning Avenhaus with VLT sphere in the near infrared, it also traces the scattered light at the surface of the disk. You can even see here the backside of the disk. So this you know, optical and near infrared wavelengths are really great to get this 3D structure, you know, because the grains are very well coupled to the gas. And then when you move to the radio, so with ALMA, I showed already this, then we are looking at a very, very thin layer of large debris, which are located in the disk midplane. And this concept, of course, translates into the dust evolution. So we start from very small submicron grains, so interplanetary dust particles here shown. These grow to dust pebbles, but yeah, before they grow, of course, they are tracing here this gas disk structure. And actually, what is a good representation of such a disk looks like is actually a sandstorm. So here is a dust storm in Texas. You see this big dust cloud, dust grains. That's exactly what's happening in protoplanetary disks. So you have the turbulence steers up these small grains, and it looks exactly like that. And then it becomes just opaque. You see here from the Curiosity rover, you have the sunstorm also on Mars. And that's exactly the picture how we have to think it in protoplanetary disk of a sort of sunstorm which just goes on for millions of years. And yeah, in sort of the midplane layer, you have then also the larger grains. And this, of course, even for Mars, it can have a dramatic effect. So this was in 2018. You could see that the whole surface of Mars was completely changing from this sandstorm. Okay, so that's about the small grains. The larger grains are settled, so we cannot see this with optical, with near-infrared wavelengths. We have to go to larger wavelengths. But there's also another effect, which is actually becomes in this picture clear. You see these rings and gaps, and now you could ask why there are these narrow rings and gaps in why they are observed. And that has to do with the radial drift. So in this picture, if you take here a dust pebble, and you have, a dust pebble rotates Keplerian, right? The dust pebble doesn't feel the pressure gradient force, but the gas feels this pressure gradient force. So the gas is a bit sub-Keplerian. So you see that this gas particle is slower, so slower than the pebble, and because of this difference, there's a constant momentum exchange. So there's always a momentum exchange between the gas and the pebble. And this effect is actually maximum if the stopping time times omega, so the stopping time of the particle, is sort of order unity. So that's what we call the Stokes number. So when the Stokes number is unity, this effect is strongest. And then what happens is that very quickly, this dust grain should fall into the star. So much, much faster than a disk is actually living. So that's a big trouble because, first we would not see any planet and we would not see any disk. So the big question was how to prevent radial drift. And the first obvious solution is, of course, to look for the regime where actually the gas velocity is exactly the same as the pebble velocity. And that is happening when the pressure gradient force is 0, and that's where dP over dr is 0. And these are actually the rings what we are looking at. So at the rings, we think that these are pressure maxima or pressure minima. I guess mostly pressure maxima, because from minima they would just drift away. And these are the locations where then the radial drift is actually not of importance anymore. So that's the idea, not only to explain these observations, but also to explain how the dust pebbles can actually grow further to planetesimals. So there are probably, these rings are sort of forming planetesimal sites in these circumstellar disks. Okay. Why I showed this, so Saturn rings, I think, is the best representation of how this pebble disk would actually look like. I mean, this system is around 10 meters high and has a width of around 282,000 kilometers. So do you see the aspect ratio is 10 to the minus 8. And actually for pebbles in protoplanetary disks, it's around 10 to the minus 6. So it's not too far off. So actually, when you think of a circumstellar disk, you can now think of a sandstorm with this sort of large pebble ring, which is included at the midplane. I think that's a very, very good representation when you think about circumstellar disks. And now you might, of course, ask why there is still the difference of 100. Well, that's easy because here there is no gas left, right? And when you have this turbulent gas, it can, of course, mix up this sort of centimeter-meter size grains very efficiently, and then you easily gain this factor 100. Okay, I was actually looking, if there was an ALMA image of Saturn, but I couldn't find one, but I found here this Uranus ring. So because it has a similar, range of dust particles, it makes sense to look also with ALMA, and here they found, at the same wavelength at 1.3 millimeter, they found here emission around Uranus. Okay. Now, when we summarize this, what I haven't mentioned is when now these dust grains settle, they create this very thin layer. And now you can imagine when you take into account the dust momentum feedback, then you give rise to a new class of instabilities. These are called dust gas track instabilities. And this is also what we wanted to study. So this is another simulation. You see, again, height over radius. And what we are looking here at is a very, very thin dust layer. So it's a bit like a Saturn ring, if you wish. You can see here that the scales are extremely small compared to the radial scale. And now what happens is this dust, settles. It wants to become a Saturn ring. And then at some point, the dust density is so large that it becomes comparable to the gas density. And that's where the streaming instability kicks in. And then you see these turbulent motions. So the streaming instability sort of gives rise to a vertical mixing. And there's now a constant, fight between, the vertical gravity who wants to settle this dust even more and the streaming instability who mixes up this dust grains. And this is probably happening at certain locations in the circumstellar disk. So that's also what we want to investigate in the future, because what is here interesting is that you can have local concentrations of the dust, and you can also form planetesimals. Okay, now moving to turbulent heating. So I haven't talked much about the effect of the dust actually for the radiative transfer, and it is extremely important. So we have to take into account the stellar heating, which is absorbed at the surface of the disk by this small grain. Again, remember a sunstorm, which is irradiated. Then you have turbulent heating, especially in these inner parts, which become optical thick. And then what we are looking at is actually the cooling, so the infrared emission. And this is also what we worked on. So here I show you a global 3D simulation now with full radiation transfer. So I include irradiation of the star under the effect of the MRI. So you see that in first order, the temperature structure doesn't change too much. You see small scale effects. So for example, small current sheets or magnetic reconnection layers, we actually can see that the temperature is heated even more. But the basic picture stays the same, so that they have a sort of temperature structure, which is due to the radiation heating. But of course, where it is important is because locally the sound speed is changed, and the MRI produces turbulent velocities on scales of the sound speed. So effectively what you do is you boost the absolute values of the turbulent velocities in the upper layer. Okay, but more about radiative transfer at the inner rim, because I wanted to explain you more about rim worlds. So let's move now to the rim worlds. So if you want to understand the temperature of the dust grain, you have to first ask, well, which radiation is absorbed and which radiation is emitted. So typically, you absorb something which is more in the optical or in the UV, and you emit something in the infrared. And now if you want to understand the temperature, you have to look at the dust opacity. So you have here an absorption opacity over wavelength. And then you can ask how strong is the UV field and how strong is the infrared field, folded with this dust opacity. And typically what you get is that these grains are sort of superheated as, if they would have the same efficiency to absorb and emit. So they are quite hot, these small grains. And this is extremely important then to determine the structure. In this model here, I show you a radiation hydrostatic model. What we do is we iterate between a radiation step and a hydrostatic step. You see again Z over R over log radius. And then you see temperature, and at the bottom you see dust density. And then step by step, we increase the dust density to the fiducial value. You see here these white lines, the tau1 line for the irradiation. And then you see this sharp transition, this sharp drop of the temperature. And that's exactly this inner rim, what I was talking about, so the inner sublimation zone. And here there's a lot of physics which come into play. So the MRI can operate in these heated layers. The MRI is damped in this layer here below, in these cold regimes. And that's where you have this very efficient dust trap, then which comes automatically because of this transition. Okay, here again a bit more in a sketch to understand this structure. So you get this sort of dust-free inner disk. You get a optical thin dust halo, which is superheated because of a temperature inversion effect. And then you have here this rim. And this rim is actually what is actually seen when you look in infrared now at these disks, because this emission dominates in the JKM bands. So when you look or when you observe these disks in the infrared, you are mostly seeing this layer here. And then quickly, the temperature drops, and the disk becomes here flared again. And here's the location, right at the outer edge of this rim, where we have this solid concentration due to this pressure maximum, the local pressure maxima. Okay, we also compared this with actually observations. You see here in this plot, these are these infrared observations of different systems. You see ring radius against total luminosity in log scale. And this color here actually represent to real data set. So this is not an error. So we just trace where the rim starts and where the rim ends. So this is this upper and lower branch. And we wanted to compare how valid are these theoretical models, or if the rim position actually makes sense, and they fit quite well. And of course you see that if you have more luminous stars, if you have more luminous stars, so you shift to radially outward because you have just higher temperatures. Okay. Very quickly, only to show you the recent model. So we try now to improve these models in a way that we try to include many constraints. We try to match the mass accretion rate from observations. We try to match the alpha value from 3D models. We try to match the ionization transition, from chemical works to tell us, how many free electrons are in a gas phase. We try to get a good representation, of course, of the stellar parameter. So these are the parameter of a young sun. We try to match the dust, the dust opacities. You can see that also gas opacities, which is still something we want to improve. But you can see we try to get most of the realistic parameter set. And this is then what we get. So if you include all this, you can get then density and temperature structures. And these we can then analyze, post-process, and then investigate, for example, where the dust pebbles are concentrated or where these planets would migrate. And then in this recent work, what we did is we tried to compare now with the Kepler data set. And Heis Mulders, helped us here. So he took all multi-planetary systems and looked, okay, what is the position of the innermost planet? And it matched quite well the position where we actually predict our pebble trap or planet trap. And it matches also the TRAPPIST-1b, so the innermost planet from TRAPPIST-1 matches also this. Yeah, and we did also more models for Herbig stars. So we would actually expect that Herbig systems have their innermost planet at a location which is a bit further out. Okay, coming to the summary. So this is the sort of picture we have right now, including the pebble planet trap here at this innermost location, the streaming instability, the vertical shear instability in the dead zone layer, and the MRI probably operating at the innermost and outermost layers. And yeah, for outlook, so that's something we are now in our group up the hill, what we are working on. So we are looking at the thermal wave instability. So we want to understand, how the absorption of the heat, what does it have on the effect on the temperature structure when you look dynamically. We're also looking at accretion bursts, because as I mentioned to you, the turbulent heating can be trapped here, and then you can have bursts of MRI fronts. We look at the dust track instabilities, especially here at the midplane layer. So we want to understand, especially in the outer disk, where dust pebbles are concentrated. And now in the future, we want to look more on the magnetic flux transport, because the radial transport of magnetic flux is extremely important to know, to understand not only the strength of this magnetic current wind, but also the strength of the MRI in these inner regions. And then we are also working on the numerical works on the GPU version of Pluto. We are building up here an adaptive mesh refinement grid for the spherical grid, and also a self-gravity module is on the way. So with this, thanks for your attention, and I'm happy to take questions. Yeah.
Thank you, Mario, for this nice and very detailed overview of disk structure and really showing us how awfully complex a physical system this is where planets form. The podium is open for questions. Henrik, wait.
Thank you, Mario. So in your plot, you show all these different instabilities, and it looks a little bit as if they were at different distances or scales from the star. But in principle, I would expect, at least from here, that the VSI and the magnetic-driven winds are at similar scales. So in your signatures, which you showed from the VSI, shouldn't the wind kind of convolute that and make the signature of the VSI harder to detect?
That's a good question. So I can probably take, let's see if I can go back quickly. Let's see if this works. So the thing is that the magnetic driven wind actually starts, or that's actually what we know, it starts at a layer which is much further up. So in this picture here, the magnetic driven wind would actually first start here. So what we found out is that actually when you look at
Hans, so what do I do? Hans,
Yeah,
I unmute you. Can you say something?
Yes. I have a little technical question. Can you hear me?
Hear you.
I have a little technical question. Since the accretion disk, the structure, you have very small scales in the inner part, larger scales in the outer part that you need to resolve in your numerical code. I assume that your time stepping scheme is explicit, so that the time steps are usually constrained to small values in the inner part, bigger ones in the outer part. Do you do tricks of say time step that is spatially variable, or what do you do?
That's a very good question. Yes. So what we typically do is twofold. So for the radiation transfer models, I showed you, what we do is we use the implicit solver. So we can crank up the time step quite high, in this implicit scheme. So we typically start with a small step until most of the temperature structure is converged, and then we slowly increase the time step to get also the sort of diffusive field in the midplane correct. But this you can only do in this sort of hydrostatic models, which I have shown you, the radiation hydrostatic models. For the full dynamical runs, you're absolutely right, and we are limited by the time step in the innermost regions. So what it practically means is that you cannot solve the full disk, from 0.1 AU to 100 AU. You have to have a sort of intermediate regime. So we typically say, the outer radius to the inner should be no more than a factor of 10. Then you can practically, sort of study the instabilities and get, sort of statistics out. But if you go beyond that, you as you say, you freeze in time effectively for the outer regime, right? So that's absolutely true. Yeah.
Thank you.
And I see that Christian Fendt, you have a question. Wait, I need to unmute. So please go.
Yeah, hi Mario. I have a question about the magnetic stellar wind from the disk. I mean, you said that the disk surface layer is ionized and is MRI unstable. So you also have a turbulent magnetic field there. So the wind, how is it driven? Is it by turbulent magnetic pressure? Because you say it's magnetically driven, and you might not have a large-scale magnetic field because of this MRI at the basis of the wind. So how do you see that launching issue,
Yeah, that's a good question. So the basic idea is, or what it comes down is the strength, of the vertical field component. So depending on the strength of the vertical field component, it directly sets you sort of where the base of the wind is launched. So in fact, what we need is magnetic flux, which, was tracked inward during the collapse. And this magnetic flux will drive the wind. So of course, if you look at Tauri stars and you're very close to the star, I mean, the picture can be more complicated because you have the stellar component. But for us, for the most of the wind evolution, which we study, it comes from this external large scale field, which actually is the seed. So it's directly proportional to the field strength. And therefore, I mentioned it at the end, it's so important to study now the evolution of the global magnetic flux, because we want to answer actually this question. Yeah.
So this global large-scale magnetic field is not
Right. I
existent
think
in
this
the.
shows that our hybrid setup actually works. We have now the same number of online questions as in the room. Do you guys want to win? Yes. Thank you. Noé. I know starting a competition always helped.
Thanks. Thank you very much for the very nice talk. As far as I understood, all the stabilities that you presented occurs at the stage where the disk mass is somewhat neglectable. And I wonder, like, if you look at a bit earlier stage, you start to have gravitational instabilities. Has this been studied in combination with the other kind of instabilities that you presented?
That's a good question. Yeah. So when you look at earlier phases where you have very massive disks, then you, as you mentioned, you have probably the gravitational instability, right, which plays a big role. So the disk, when one says it gets too unstable, you have a strong Reynolds stress, right, which would also drive the angular momentum. And this is actually a phase, what I mentioned at the very beginning, when you have this strong bursts, of accretion. That's probably the phase where, the envelope still feeds the disk and also supports, the sort of self-gravity or the gravitational instability. So the question is, how long does this phase last? So this is unknown, right? We focus more on the sort of class 2 stage, so the stage where the envelope is gone, where the effect of the GI is less. But you're right. I mean, if you look, especially if you look at young systems, I mean, this is a big, a big or if important step you should include.
All right. I see no more questions, neither online nor in the room. So before we close the colloquium and thank Mario, let me make the announcement of next week's colloquium. We will have another local speaker, Andreas Sander, now not from up the hill, but from the Astronomisches Recheninstitut, so from the Center for Astronomy. He will talk about stars with the title Deciphering the Properties and Impact of Hot and Massive Stars with Detailed Stellar Atmosphere Modeling. So we will also hear about radiative transfer, complex chemistry, and interesting astrophysical systems. With that, we don't have, because Mario is local speaker, drinks and dinner, but you know where to find him. And if you have further questions to this field, to his talk, please get in touch with him. Mario, many thanks for this really exciting talk.
Thanks.